This is the review for AP Chemistry Unit 4, and these are the topics for today. So first is the intermolecular forces, and they are the physical bonds between the molecules. They're much weaker than the intramolecular forces, which are the forces between the atoms. And the three main types are the hydrogen bonding, dipole-dipole forces, and London dispersion forces. And we will go over each of them today. First is the ion-dipole, and they are between an ion and a polar molecule. It's when a soluble ionic compound is mixed in polar liquids such as water. So this is an example when a salt or NaCl dissolves in water. It dissociates into Na plus and Cl ions, and they will each attract the water molecules. But Na plus will attract the oxygen atoms because they are partially negative, and Cl minus ions will attract the hydrogen atoms because they are partially positive. And Na plus attracts more H2O molecules because it's smaller and there will be more force of attraction between the ion and water. And Cl minus will attract less water molecules because more shielding effect is there because it's larger. Nucleus cannot attract H2O as well as Na plus. And Coulomb's law applies. If cation and anion attractions are stronger than the ion dipole, compound will be insoluble. It will not dissolve in water because the ion attractions are stronger, so they will attract each other very strongly that water molecules cannot pull them apart. And this is another example. We are comparing magnesium hydroxide and barium hydroxide. And magnesium hydroxide is insoluble, so it does not dissolve in water. It is because there is a large force of attraction between magnesium ions and hydroxide ions, so water molecules cannot pull them apart. But beryllium hydroxide is soluble, so water molecules can pull them apart. The lattice energy is the energy required to separate an ionic compound into ions. And smaller the ions are, there will be more force of attractions, and the larger the lattice energy will be. Because if the ions are smaller, they will attract each other more strongly, and it will be harder for us to separate them into ions. And we have a diagram here. Ionic bond, the ions attracting each other very strongly, and the ion dipole intermolecular forces, so water pulling them apart. Next, IMF is the dipole-dipole forces, and they are between two polar molecules because it's dipole and dipole forces. They are relatively weak. The more polar the molecules, the stronger the IMF, and the lower the potential energy. Because as the molecules are more polar, they will attract each other more strongly, and the distance between them will be shorter. So potential energy is like the distance between them. So as the distance between them is shorter, the potential energy will be lower. So this represents the high potential energy, larger distance, and this represents the low potential energy, a shorter distance. Next IMF is the hydrogen bonding. It is a type of dipole-dipole, but it involves a hydrogen that is covalently bonded to F, O, or N, and another F, O, or N. And it is 5 to 10 times stronger than other dipole-dipole attractions. It is because FH, OH, or NH bonds are very polar because fluorine, oxygen, and nitrogen are very electronegative, so they attract hydrogen ions very strongly, so it will be very polar. And atoms are very small, so they can attract the hydrogen atoms very strongly. And they have lone pairs, which allows fluorine, oxygen, or nitrogen atoms to attract the hydrogen more strongly, like in this case. And you have water, a very common example of hydrogen bonding. And hydrogen bonding occurs between a hydrogen and an oxygen of another water molecule. And this is the intramolecular polar covalent bond, while this is the hydrogen bonding, the bonding between two water molecules. So between the molecules. And oxygen has a lone pair, so there will be stronger attraction for a positive hydrogen atom. and it accounts for high boiling point of water because it will be harder to break the bonds between water molecules because of this very strong dipole-dipole forces of hydrogen bonding. And as the number of hydrogen bonds increases, the boiling point increases because if there are more hydrogen bonds between two molecules, it will be even harder to break those two bonds and then separate them into individual molecules. Also, if the size increases, the boiling point increases, and if the molar mass increases, the boiling point increases as well. Next is the dipole-induced dipole forces, and it's when a polar molecule induces a dipole or a polarity in a non-polar molecule. So even you are non-polar, a polar molecule can come near you and then excite the electrons and then make you polar. So electrons in non-polar molecules are attracted to positive end of the polar molecule. So as the electrons in non-polar molecule get attracted to the positive end, they will be polarized. And strength of dipole-induced dipole forces increases when non-polar molecule is larger because it will be more polarizable. The last type of IMF is induced dipole-induced dipole, aka London dispersion forces. It is also known as LDF, and it occurs between all species, so atoms, ions, or nonpolar molecules. So without the LDF, all nonpolar species would be in gas phase when some are not. Actually, Br2 is a nonpolar molecule, but it is in liquid phase at room temperature because LDF exists and there are force of attractions between molecules. The greater the surface area, more polarizable the molecule, and more energy it will take to turn the molecule from liquid to gas. Because, as I just mentioned, for dipole-dipole, if the molecule is large or has a greater surface area, there will be more space to polarize the molecule. So the molecule will be more polarizable and there will be a stronger force of attraction between them, and it will take more energy to turn it from liquid to gas. And the molecules that only have LDFs are diatomic molecules like Br2, Cl2, and noble gases, and hydrocarbons. This is the order of IMFs from weakest to the strongest, and the strongest is ion-dipole. So when a soluble ionic compound dissolves in water, the water molecules separate them, and then those ions attract the water molecules as well. The next is a hydrogen bond. So a type of dipole-dipole, but the strongest type, and then the dipole-dipole, and then ion-induced dipole, when an ion induces polarity in a molecule. Next is a dipole-induced dipole, so polar molecule induces a polarity in a non-polar molecule. And the weakest type is the London dispersion forces, and they are the only IMFs that non-polar species have. And for LDFs, larger the molecule, the more polarizable the molecule, and there will be more force of attraction. So it will be hard to break the IMFs between them, and the boiling point will be higher. The last topic for today is the enthalpy of reaction. Breaking bonds are endothermic because energy is required to break the bond. And as you break the bond, the atoms will get separated and the distance between them will increase and the potential energy will increase as well. And bond enthalpy is the energy needed to break 1 mole of bonds in gaseous molecules. Forming bonds are exothermic instead of being endothermic for breaking bonds because as you form the bond, the energy is released and potential energy decreases because the distance between them gets shorter as you make the bond and atoms get together. So the same amount of energy absorbed when breaking the bond is released when you form a bond. Next, you have to know how to calculate the enthalpy of reaction, and how you do that is using this equation right here. So the enthalpy is equal to the sum of all bound enthalpies of bonds broken minus the sum of all bond enthalpies of bonds formed. So you basically have to add up all the bond enthalpies for reactants, because reactants are the bonds that get broken, and then minus the bond enthalpies of bonds in the products, because you form the bonds in products. So we have an example here. So you have 4 CH bonds here. So you go to the chart and then find the bond enthalpy. So you have 4 CH bond, and then you have 1 O double bond, which is 495. And these are the bond enthalpies for reactants, and then you do minus the bond enthalpies for products. So you have 2 CO double bond, which is 799, and then you plus, you have 2 OH bond, which is 463, and then you do the calculation and you get negative 808 kilojoules per mole. You cannot forget the unit of kilojoules per mole, and the negative enthalpy means that the energy is released and it was an exothermic reaction. I have another example here. So first, if they give you the reaction, you first have to draw the Lewis diagrams for each of the molecule, and then you do the calculations. So you first have to find all the bond enthalpies of bonds broken in reactants. So you have 4 CH bonds. 4 CH bonds, which is 413. Then you have 1 carbon double bond, which is 614. And then you have 1 hydrogen-hydrogen bond, which is 436. And then you minus all the bonds in products, which is 1 carbon-carbon bond, which is not shown here, but it equals 348. So 348 plus you have 6 CH bonds. So 6 times 413. Then you do the calculation. You get negative 124 kilojoules per mole. So it also means that the reaction was exothermic, which released heat, which gives you the negative sign in enthalpy.